Let's just jump right in. Welcome to the Explainer. I'm really thrilled you're here. Today, we're going to take a calm but honestly fascinating journey into a hidden world that you literally carry around with you every single day. We live in an era where portable energy is, well, it's just expected, right? We plug things in, we unplug them, toss them in our bags, and they just work. But beneath those smooth glass screens and sleek metal cases, there is this silent, incredibly beautiful dance of chemistry happening. So get comfortable and let's unravel the secrets of portable power together.
Take a second and look at the device you're probably using right now, or maybe the phone resting on your desk. Have you ever actually stopped to wonder what is happening inside that little battery as it quietly powers your screen, your apps, your entire connection to the world? I mean, it's completely silent, zero moving mechanical parts, and yet there's a massive coordinated migration happening right there at a microscopic level. It's a modern marvel that we kind of take entirely for granted.
The secret to all of it, from the tiny battery in a smartwatch to the massive battery packs powering electric cars, is beautifully simple at its core. It is all about controlled chemistry gracefully moving electrons from one place to another. We're going to look at the elegant mechanics of how we basically bottle up lightning. We'll touch on classic wet cells and look closely at the really fascinating mechanics of Zinc-Air technology, all without getting bogged down in crazy textbook jargon.
Part 1. The anatomy of a battery, or really, the core engine of it all.
Long before we had complex lithium-ion packs, we had the galvanic cell. This is the fundamental engine behind all our batteries. In the absolute simplest terms, it's a system where a spontaneous chemical reaction happens, specifically an oxidation and reduction reaction, and we capture the energy of that reaction as electricity. It turns chemical potential directly into electrical power. It's basically nature just wanting to find a balance, and us cleverly sticking a wire in the way to harness that desire.
Every battery needs a specific cast of characters to actually work. Think of the anode as the source. Its job is releasing electrons. The cathode is the receiver, capturing those released electrons. Between them, you've got the electrolyte. This is a medium that acts like a transit system, allowing charged particles, or ions, to travel back and forth. And finally, the separator. It acts as a selective barrier to prevent a short circuit by keeping the chemicals from mixing directly while still letting the necessary ions pass right through. So looking at these components in action, let's take the classic zinc-copper cell. On one side is our zinc anode, releasing electrons. That flow of electrons traveling up and through the circuit is literally the electricity that powers our devices, eventually reaching the copper cathode on the other side. Meanwhile, down in the liquid electrolyte, ions are gracefully moving through a salt bridge in the middle to keep everything perfectly electrically balanced. Now, this exact property of zinc easily releasing electrons is exactly why it's the star of the modern Zinc-Air battery. In a Zinc-Air setup, you have a very similar zinc anode acting as the fuel, but instead of a heavy copper cathode, it uses a porous carbon structure that literally breathes in oxygen from the air to complete the reaction. How cool is that?
Moving on to part 2, primary cells. These are your one-and-done batteries.
A crucial thing to remember here is that not all batteries are created equal. We generally categorize them into two main camps. Primary batteries are designed for a single use. Once that chemical reaction is complete, they're disposed of. Secondary batteries are the rechargeable ones, capable of playing their chemical reaction forward and backward over and over again. A perfect everyday example of a primary battery is that Zinc-Air cell we just talked about, which is heavily used in hearing aids or medical monitors. Because it uses outside air rather than packing heavy chemicals inside, it holds a massive amount of energy for its tiny size. But once that zinc is fully oxidized, it's done. Think of a primary battery discharging as a one-way street. The reaction goes from material A to material B, sending electrons through your device along the way. Once material A is depleted, the battery's dead. But a secondary battery, that's a two-way street. It discharges to give you power, absolutely, but when you plug it into the wall, it forces the electrons the other way. It literally reverses the chemical reaction and resets all those active materials.
Which brings us to section 3, the absolute magic of recharging.
The grandfather of rechargeable batteries is probably sitting under the hood of your car right now, the lead-acid storage cell. It provides a really rugged, heavy-duty contrast to those super lightweight Zinc-Air cells we just looked at. It relies on heavy lead plates interacting with a bath of sulfuric acid. As you drive, the car's alternator charges it, and as you start your car, it discharges. The lead and sulfuric acid gracefully interact, combining into lead sulfate when discharging, and then literally breaking apart again when charging. Our source material actually describes this process beautifully. It notes that when we recharge a battery, we are essentially operating it as an electrolytic cell. What that means is,
We are the ones supplying the energy from an external source, like the power grid. By aggressively pushing energy back into the system, we are forcing the chemical reactions to run backwards. We're physically resetting the stage for the next performance.
Now, the battery powering the modern world, what's in your phone and laptop right this very second, is the lithium-ion cell. Unlike older batteries, lithium-ion cells don't actually rely on true oxidation and reduction reactions in the traditional sense. Instead, they operate on a clever principle of transport. You've got layers of graphite on one side and lithium cobalt oxide on the other, and the lithium ions, they simply commute back and forth through a polymer gel right between those two layers.
Let's quickly break down how simple and honestly elegant this charging process is. Step 1, you plug your phone in, which applies an external voltage. Step 2, that pressure forces the lithium ions to abandon their home in the positive electrode and travel across the separator into the layers of graphite. Step 3, the electrons take the long way around through your charging cable. And finally, step 4, the ions and electrons are stored in the graphite, packed tight with potential energy, and they just wait, ready to be deployed the exact moment you unplug the device. Section 4. Looking beyond batteries at fuel cells. There is a really profound difference here. A standard battery is basically a closed box, right? It only has the chemicals packed inside it at the factory. But a fuel cell, it never dies as long as you keep giving it fuel. It functions way more like an engine that runs on chemistry instead of combustion. This concept of pulling fuel from the outside is actually the exact same magic behind the Zinc-Air batteries we were talking about earlier. By pulling oxygen directly from the atmosphere to use as a reactant, they beautifully blur the line between a traditional sealed battery and a continuous fuel cell. A perfect example of that continuous flow is the methanol-oxygen fuel cell. Instead of relying on a closed loop of lithium or lead, this setup allows liquid methanol and oxygen from the air to continuously flow in. They react at specialized electrodes, release electrons to power a device, and produce nothing but harmless water vapor and carbon dioxide as exhaust. Because they are so incredibly efficient, this tech is increasingly being used to provide continuous, hyper-reliable power for things like remote communication arrays or even space exploration.
And finally, Section 5, a peaceful closing thought.
You know, it is so easy to just see our devices as magic black boxes made of glass and aluminum, but by understanding this simple anatomy, the anodes, the cathodes, the graceful movement of ions and electrons, we totally demystify that magic. You literally carry the power of highly orchestrated, controlled chemistry in your pocket every single day. It's just a massive testament to human ingenuity that we've tamed these elemental forces so completely that they quietly and seamlessly serve us in the background. So, I'm going to leave you with this thought. Tonight, the next time you plug in your phone before you go to sleep, take just a brief moment to visualize it. Appreciate the billions of tiny lithium ions flowing back to their graphite homes, getting ready to power your tomorrow. It really makes you wonder, what else in your everyday surroundings is secretly powered by the simple, beautiful journey of an electron? Thanks so much for hanging out with me for this explainer. Keep learning and keep wondering.